So in this session, we'll have a look at a feature which is unique to 80486, which is going to be burst transfers. We have already talked about the concept of burst transfer. When we talked about the pinout of 80486, we said that during a burst transfer, 4 words of data, that's 4 32-bit data, will be transferred one after the other within a period of 5 clock cycles. So what we will see is how does this burst transfer takes place. So burst transfer, as I said, takes place within 5 clock cycles. Within 5 clock cycles, 4 words of data will be transferred. So when I'm talking about word here, I am talking about a 32-bit data. So 4 32-bit data will be transferred in 5 clock cycles. So these are the 5 clock cycles, T1 and 4 T2s. So what happens is during T1, the address is going to be generated, and assuming that whatever is our memory is going to be fast enough, responds with the data. So with the address, we also know that the ADS signal is going to be activated. The ADS signal is going to be made low during T1 data, and what happens is every time the memory is going to be ready, it makes the burst ready signal low. And when the burst ready signal is low, it means data is available. So the first 32 bits of data D0 will be available. During T2, the next address is going to be generated. So after this address has been generated, once again the memory will respond with a bus ready signal indicating it is ready with data, and the data transfer takes place. So then the third address is going to be generated, and again the device or memory responds with the burst ready signal going low. The data is going to be available, or the third 32-bit data is going to be made available. The fourth address is going to be generated. Once again, memory indicates it's ready with data by making the B ready signal low. The fourth 32-bit data is going to be generated. So T1, T2, this is how it is going to be done. So we have one T1 which is followed by 4 T2 states. So during the first T1, the first address is going to be generated. With the address strobe signal will be made low. After this, the address strobe signal is not going to be made low. The burst bus is generally associated with the cache transfers because cache can respond with data very fast. So when the address is generated for the first T state, the ADS signal is made low. And what happens is the bus ready signal will be made low by the memory device indicating it's ready with data. It gives the first 32-bit data. Then the second address is going to be generated. The second 32-bit data will be given along with the bus ready signal by the memory device. The third address is going to be generated, and then again the burst ready signal goes low. The third 32-bit data is going to be given. Fourth address will be generated. Burst ready signal again goes low. And the third or the fourth 32-bit data is going to be given. So in 5 clock cycles, 4 32-bit transfers are going to be completed. Now, how is it possible that 4 32-bit transfers can be completed in one cycle? As I said, first this is generally done with the cache, and cache is going to be a very fast memory. And you can see as soon as address is generated, it's going to respond with the data. How does that happen? It happens because the memory chip will already be selected, and whenever we are talking about 4 32-bit transfers, we are going to be talking from 4 consecutive locations. So if the first transfer is going to take place with address 000, it is going to be a 32-bit address. So if it takes place with address 000, the next address would be automatically 004, with which the data transfer will take place. The next part of the burst is from 008. The next burst is going to be from 00C. So the burst will be taking place from continuous data locations. So since they are going to be taking from consecutive data locations, what is going to vary is only the last nibble of the address. The rest of the address is going to remain same. So it means that whatever was the chip enabled circuit would have already been activated, and what is going to happen is only these addresses are going to change. So since only the last nibble of the address is going to change, the memory is already ready. It is already enabled. All it has to do it has to place the data on the data lines. The next burst similarly will be from address 10 onwards. Then it means that 10, 14, 18 and 1C are going to be involved in this burst transfer. So since only address lines A0 to A3 need to be varied in this particular case, the memory is also aware only that A0 to A3 is going to change. So it will be able to provide the data far quickly than it is able to do if you are doing a very random access. For instance, if I am doing an access to location 000 and then do an access to location 0100, of course it will take time because you might move from one memory chip to another memory chip. But here, since we are talking about 4 consecutive locations, they are all will definitely be in the same memory chip, and the memory chip would have been enabled already. All it has to do is it has to pick the data from consecutive locations and give it. The rest of the control circuitry of the memory will already be activated. So memory will be able to respond very fast here. So this is burst transfer, which is available generally with 80486 because 80486 supports internal as well as external cache, and cache memory can actually respond at this speed. And also we have the advantage that the only lines that are going to change are address lines A0 to A3. So this is the burst transfer of 80486. I will stop with this in this session.